Hello everyone, my name is Dapeng Lan from University of Oslo. Today I'm going to introduce our work, a federated for cloud framework for data processing and orchestration, a case study of smart screen wall in smart cities. The wall is elaborated together with my colleagues Yu, Hamir, Frank, Stefan, and Lade. So here is the agenda of the talk. I will introduce the backgrounds, the related work, the architecture and orchestration framework, the system implementation, and then evaluation, and then come to the conclusion and future work. As we all know, Internet of Things application has been evolving in various domains. Smart city is a promising representative. Conventional smart city services typically centralized. For example, data storage, data analytics, and feedback solely relied on remote server in cloud. However, traditional cloud infrastructure cannot fulfill the performance requirements of the rapidly emerging applications such as smart city, virtual reality, autonomous driving, and smart grid automation, all demanding high throughput and ultra-low latency. In the fog computing and mobile computing paradigm has been proposed to address the low latency and high throughput challenges by migrating cloud services to the proximity of the local infrastructures to guarantee the low latency applications and increase the quality of services. However, different from cloud computing, fog computing nodes are heterogeneous in terms of hardware resources. And also, due to the large number of fog computing nodes, the computing framework requires a proper abstraction layer to manage these nodes. And also, the hybrid approaches combine both fog computing and cloud computing require deploying two different process engines. How to synchronize and how to split the data processing workflow become a problem. In this work, we are going to provide a real implementation and validation of the federated fog and cloud framework for data processing and orchestration in smart cities, contributing valuable inputs to the related research fields. This is because traditionally the cloud data processing platforms like Mapper, Reduce, and Spark, they only consider the cloud IoT solutions and still far away from the general data processing frameworks working across cloud and fog platforms. And also, there are some existing fog and edge cloud-based data processing and orchestration frameworks. However, they are not general frameworks and they need specific interfaces and use different standards. In our case, we are trying to address these issues. This figure shows our architecture design and orchestration framework. As you can see, there are three layers in our system design: the cloud layer, the fog layer, and the end devices layer. The end devices layer consists of different kinds of sensors and actuators in different user scenarios, such as smart building, smart traffic, smart green board. And the fog layers usually is lying between the end devices layer and the cloud layer. And also in the cloud layers, they usually have more computing resources and storage resources. Our design principle creates a data flow pipeline for application across different layers, which hides the complexity for application developers, as they do not consider the heterogeneity of underlying service devices. How can we do that? As the figure shows, we create the process element model here. The process engine can be deployed both in end devices, fog layer, and cloud layer. And they are the fundamental elements for the applications. As you can see details for the process engine, it consists of different layers as well. The hardware layer, virtualization layer, orchestration layer, data management, communication, and data input, output, and process. And the top is the application. according to the characteristics of the application. There are also different characteristics between the end devices and the cloud devices. For instance, in the end devices, they are usually more heterogeneity and they are more large scale. And in the cloud layer, they are more small scaled and they have a low heterogeneity. In this table, we shows the details about the process engine, which consists of different layers. The hardware layers is consists of heterogeneous devices, has various kinds of resources. For example, computing resources, storage resources, and network resources. The virtualization layer can consist of different kinds of virtualization technologies. Here, the highest complexity of the hardware heterogeneity. In the orchestration layer, this layer is responsible for deploying services on the corresponding devices. The data management layer addresses the data storage and distribution, including file systems, database, caches, and data lakes. The analytical engine layer deploys the application-specific processing framework for running the tasks and jobs, which are usually divided into two categories, batch jobs and stream jobs. The communication interface layer. This layer is responsible for message communication and data exchange, usually equipped with publish and subscribe message system. Finally, the application layer. This layer defines the object and logic of the data processing jobs. For instance, the cloud layer usually deals with complex event processing, streaming and batching applications, and virtualization and monitoring applications. Here we shows how we combine this process engine together using the process engine data flow. Process engine data flow is a directly acyclic graph of process engine, and each application has its own process engine data flow. Each process engine mainly contains of three kinds of data process model: data inputs, data process, and data outputs. The data input means receiving the data from the environment. The data processing combines different analytic and storage techniques. And data output will output the data to the next process engine or output the data to the next level of the application. As figure 3 shows, by connecting the process engine from different layers, this process engine forms an execution process for the application. When designing this process engine, there are some principles need to be considered, like the independency, priority, and standard. We are focused on the detailed implementation and the data processing orchestration framework in this slide. The core of our proposed data processing framework is to explore the semantic of both the cloud and fog platform in order to provide a user-friendly orchestration framework. Table 1 shows the test bed parameters and the performance metrics. We use Raspberry Pi as our end devices and fog node, and then we use our cloud platform, a Norwegian cloud infrastructure for research and education cloud platform. The Raspberry Pi is equipped with various kinds of sensors, such as temperature, humidity, light sensors. It's mounted at the top of the green wall. Here shows the details of our implementation. The application, we use the cloud for virtualization and fog for IoT streaming and signal control, and end devices for real-time sensing. In the data analytics, we use Apache Flink, which is a distributed stream processor, which also supports batch process. Apache Flink has intuitive and expressive interface to enable various stateful and stateless data processing services. The communication interface, we use MQTT, a lightweight publish and subscribe protocol. And the Apache Kafka is also used. which is an open source stream processing software platform. In the orchestration layer, we use Kubernetes, which is an open source container orchestration system for automating application deployment, scaling, and management. We then use virtualization techniques. Container is a standardized way to package software components and their dependency, which helps this application to be easily deployed and reproduced. Here shows how we set up the testbed and the system. We use Docker build feature to create customized Docker for our components, such as Apache Flink, MQTT, and Kafka. After that, we use Kubernetes to compose the services running on the cluster, across in the cloud and fork nodes. We wrap the components by YAML script, which defines where the service is deployed and how much resources is utilized by each services, and connection between the services and the network configurations. Benefiting from the combination of Docker and Kubernetes, the developer can easily develop the application component without worrying about the hardware layer. This figure shows our evaluation for our system. Previously, the function of Greenwall was solely relied on our public cloud based on monitoring and management solution. Here, we're trying to explicitly partition the task between the fork nodes and the cloud. In the edge side, it's mainly used for sensor measuring and lightweight data pre-processing, and also for monitoring and control, and timely feedback control in abnormal situations. In the cloud, we usually use the function graphic visualization and long-term data storage. And also, we can use the machine learning model, which can be trained in the cloud and deployed in the fork node. This figure also shows our visualization panel, which shows the data collected from the temperature, humidity, light, PM 2.5, and carbon dioxide sensors. After that, we implement the machine learning model LSTM algorithm that is used for abnormal detection of indoor climate in both cloud and fork nodes, and we compare the results. The training time consumption in the cloud is 252 seconds, which is much less than the training time, which is more than 2,000 seconds cost in the edge node. The prediction time in the cloud is near 12 million seconds, and the fork side needs to be up to 87 million seconds. Here shows the cloud benefits from the more computational resources than the fork node. Machine learning tasks take full usage of the computing resources in the cloud node, leads to above 90% of CPU load of a single node processor in both training and prediction process, while the fork node equipped with an embedded 4-core processor can hardly shift more computing resources to improve efficiency. Lastly, the memory usage. The cloud fork node utilizes 81% of assigned 4G memory in both training and prediction process, while the fork node consumes near 90% of its 1G memory, which further enlarges the performance gap. Let alone the computing resources in the cloud can be flexibly scaled if necessary. This figure shows that using the Federated Cloud Fork platform can efficiently reduce the latency and improve the system performance. The figure A shows the comparison of on-node processing time between fork and cloud nodes. The x-axis indicates the number of performance tests, while the y-axis denotes the on-node processing time. The result shows that the on-node processing time in the fork is larger than that in the cloud, as the cloud platform has more resources to process the tasks. Figure 9 shows the comparison of the round trip time between fork and cloud nodes. It shows that the average round trip time for the cloud is near 65 milliseconds, while it's larger than that of fork side of 33 milliseconds. The reason is that fork node can are closer to the field node as compared with that of the cloud platform. Here also shows the machine learning model can be trained in the cloud platform to take full advantage of the computing resources, and the training model can be then transferred and deployed on the fork node to guarantee a low latency decision making. In conclusion, we propose a distributed and fork cloud data processing and orchestration framework, and exploiting the semantic of both the cloud and fork platform. We explain the detail of the framework design, logic, components, and functions, and framework implementation. Our real-world smart green wall application demonstrates the effectiveness of the orchestration framework, integrating the cloud and fork node. In the future work, we will investigate the dynamic service configurations in the fork cloud data processing and orchestration framework. Thanks for your listening.